Okay, good afternoon. I'm Dean Eckles from MIT Sloan. Today I'm gonna talk a little bit about also statistical and causal inference and networks, sort of what we've been talking about so far, but from a slightly different perspective in that I'm going to focus on finite sample inference and networks for the similar kinds of quantities that you were just talking about, the effects of interventions in networks that potentially have spillover effects. And so we have a paper, working paper on this topic, exact p-values for network interference. This joint work with Susan Athey and Hito Evans from Stanford. When we think about what our goals could be in a lot of this work, there's a few different possible goals. We could be testing for estimating endogenous peer effects, answering questions like how does a marginal peer in my network affect somebody's adoption, somebody's outcome. We could be interested in testing for estimating spillovers, or sometimes these are called exogenous peer effects. So that's what Oleg was just talking about. How does treating a peer affect your outcome? And we could also be interested, and this is related to both of these, interested in estimating effects of some kind of global intervention. For example, some global static intervention like treating everyone or treating no one. And so those are both potential goals here. Actually, what I'm going to focus primarily on is just the second goal, testing for or estimating spillovers in the network. And so I think this is actually the simplest case of those three things. So basically, how can we tell if the outcome of a particular vertex is affected by the treatment of their peers or network neighbors in some sense? There's kind of plenty of jargon for this. Sometimes these are called spillovers. These can be called exogenous peer effects or interference. Maybe there's other names too. So we've switched back and forth between what we call them in our paper. So I think the current version of the paper has interference in the title, and then mainly in the text we say spillovers. But these are all the same thing. So one idea is if we've actually randomly assigned treatments to vertices in our network, then this might seem like actually a pretty easy problem, like just detecting whether my outcome depends on the treatments of my neighbors. It turns out that actually it's not that easy of a problem. I mean, so we just kind of worked through the whole TMLE exercise for that, and I know this is a problem that other people have been working on. So we try to tackle this in a somewhat restricted framework of doing Fisherian randomization inference, and that's what's going to allow us to do finite sample exact inference. So in order to set that up, because I think that some of these tools may not be as familiar to this crowd, at least everyone, is to think of an even simpler case, and this is what we just did in the previous talk, start with the IID case and work from there. So how could we actually tell whether a unit's outcome, a vertice's outcome, is affected by its own randomly assigned treatment, right? So that is, how can we just estimate or detect treatment effects? And so one of the things that we're going to try to do here is actually do exact distribution-free inference. And so what we care about is, in this context, are some causal quantities where we have the outcome for a unit when they're treated, an outcome for a unit when they're in control, and we probably care about some kind of summary of these delta i's, the difference between their outcome under treatment and under control. I think I've now homogenized these slides to use W as the treatment. Unfortunately, in conflict with the previous talk, W will be the treatment. And so we'll sometimes write this more elaborate form where yi depends on wi, right? So that we have a potential outcome for each possible w for each unit, right? So the idea here is that we have this fundamental problem of causal inference, which is that for each unit, we're going to observe each vertex either treated or not treated. And so the kind of fundamental problem of causal inference is that we have all this missing data that we care about. So it's not going to be possible for each unit I for us to actually observe both of these things and estimate this. But it might be possible for us to still estimate summaries of these quantities and do inference about summaries of these quantities. That's the fundamental problem of causal inference. And one way of thinking about this is we can imagine this setup, a basic case where we have 6 observations from a randomized experiment. So these are 6 individuals. And then for each individual, we randomly assign them to treatment. So these 3 people got control, and these people got treatment. And then we observe their outcomes under those, right? So what's going on sort of under the hood in this potential outcomes causal inference framework is that each unit has a potential outcome under control and a potential outcome under treatment, and we're just sort of observing only some of this table of potential outcomes. So there's a bunch of missing data, and that's where uncertainty, if we're trying to do, say, finite sample inference, even finite population inference for the treatment effects in this population of 6 units, comes from, is the idea that we're missing some of the data that would allow us to know the treatment effects. The approach that dates back to Fisher here is to do randomization inference under a sharp null hypothesis that there are no treatment effects whatsoever. So that is that we fill in these potential outcomes under the null hypothesis with the potential outcome that we observed under the other condition, right? So under the null hypothesis that yi0 equals yi1 for all units, we can fill in this entire table of potential outcomes. This is sometimes what is meant by the term a sharp null hypothesis, and that we're actually able to complete this entire table of potential outcomes. So when we have a sharp null hypothesis of this kind, that the treatment has no effects whatsoever, then we can actually infer all the potential outcomes from the observed outcomes. And note that, I mean, here, since I've talked about this basic case of without the network yet, we're assuming that there's no interference between units. That's what allowed us to basically say that, OK, as long as your treatment is unchanged, as long as wi remains the same, then 2 vectors of treatments for the entire network, w and w prime, don't change your outcome. That is that this sharp null hypothesis here defines a certain type of a level set for this function yi. And in general, we can think about null hypotheses here as defining level sets. Okay. So then the way we can go about doing randomization inference here is we can imagine all the possible treatment assignment vectors for these 6 units. So this is the treatment of unit 1, treatment of unit 2, under a bunch of different possible treatments. In fact, all of the possible treatments. And for each one, we can compute something like our test statistic, like the difference between treatment and control in their average outcome, for example, or some difference in ranks, for example, right? And so we under this null hypothesis, we actually have the entire randomization distribution is known to us. We know what the distribution is of the test statistic for this finite population. So that allows us to do exact inference. That is, we can compare our observed test statistic to the distribution of test statistics under our known randomization. Usually, there's a lot of possible randomizations, so we don't actually compare it with all the possible randomizations. We sample some of them, right? So this generates a permutation test, right? But this is a particular kind of framework and basis for reasoning about why a permutation test is going to provide exact finite sample, finite population inference here. So this is kind of the normal recipe of Fisherian randomization inference, right? Is that we choose some test statistic that detects what we care about, like a difference in means, difference in log means, difference in ranks between treatment and control. We compute the observed value of this test statistic. We note that under the sharp null, no matter what w is, in this case where the treatment has no effects whatsoever, y remains the same, right? So we can just think of our observed y is the y we would have observed under any treatment vector whatsoever. Then we can draw a permuted treatment vector consistent with our original randomization, compute the value of test statistic under that permutation. Notice that here we're able to evaluate the test statistic using our observed y because of this sharp null, right? And then we repeat this process a bunch of times to produce our permutation test. Okay. So yeah, so the basic idea here is that this is this reasoned basis for inference where really all we have to know is the process by which we randomly assigned our treatment vector w. So often this is going to end up corresponding to a permutation test, and these tests are exact. That is, the tests have the correct size. The type 1 error rate is less than or equal to the nominal rate, and we don't need any distributional assumptions whatsoever except for our assumption on w, which hopefully we randomized ourselves or my friend randomized, and there's some data that suggests that they really randomized it in the way that they said. Okay, but we do need a sharp null hypothesis. And this is going to be important for the context of detecting spillovers in networks. So causal inference for spillovers, we want to tell if my outcome is affected by my peers' treatments. And so a simple case here can help reason about this a little bit. Think if our population consists of isolated dyads. So we have a network that has n over 2 connected components. So then we can think about whether the outcome of one member of a dyad depends on the treatment of the other member of the dyad. Right? So that's pretty simple. So here, at least we know that the dyads are totally independent of each other. And so we could imagine just inference based on the independence of the dyads. But in a lot of other cases, we perhaps have a single connected component, or at least there's a giant component that includes most of the vertices in our network. And so we're going to try to do inference in this case. So each unit could be affected by actually all other units' treatments. So that can make, you can make some assumptions that maybe they aren't affected by other units' treatments if you especially have one time step, right? So if we observe outcomes immediately after treatment, then I'm only affected by my own treatment and my neighbor's treatments. But if you allow time to start running, then everyone could be affected by everyone's treatment. So, so we'd like to still be able to do inference in this case. And so here, we're going to have the same kind of causal inference setup, but we care about whether your peer is assigned to control or not. Okay. So the setup here is that we have this finite population of units. These units are connected with some adjacency matrix A. And then we measure potentially covariates X as well. So then we have this n vector W. That's our treatment assignment. And so for each unit, then there's a set of potential outcomes, YIW, one for each of the possible W's, right? Now notice here that I no longer have YIWI, but in fact, there's a potential outcome for each unit for every possible global treatment assignment vector, right? So we've just had a combinatorial explosion here, right? So then we're still interested in these causal comparisons, these comparisons between potential outcomes for 2 different possible treatment vectors. So some of the null hypotheses that we could be interested in here are things like no treatment effects. This is the sharp null that we started with, but now we're in a network, so that's like, okay, that YIW equals YIW prime for all W and W prime. So this is the same hypothesis we had before, and actually you can apply this normal randomization inference method to get exact inference for whether there are any treatment effects whatsoever. You might want to use potentially a different test statistic, but the inference will be valid no matter the choice of the test statistic. But we'd really like to be able to test things like this, like no spillover effects. So here we have this sort of level set idea that basically YIW equals YIW prime as long as the ith unit of W and W prime is the same. So as long as my treatment doesn't change, it doesn't matter what happens to the rest of the treatment vector, we can test that null hypothesis. So that's going to be the primary goal that I'm going to focus on, though all the theory that we do also applies to these things like no higher order effects. So we could allow for there to be first order effects, and then we could test the null hypothesis that there are direct effects, first order effects of friends, but no higher order effects. Okay. So one thought is you could just sort of apply the normal machinery of randomization inference here. And so you could just do your permutation test just as you did before, just according to that recipe, but to test for these spillovers. How would that work? Okay, so that's actually what some of my colleagues who are great, but I'm just criticizing this particular thing, did in this well-known Nature paper about a randomized experiment on Facebook. Where they have this get out the vote message on Facebook, and you can see whether this actually causes people to vote, because voting records, whether people vote, are public in the US, and so you can join the data and see whether people vote. So they say the messages not only influence the users who receive them, but also the user's friends and the friends of friends. So where does this evidence come from? Well, essentially, they're able to say, okay, for close friends, that is user-friend, high deciles of user-friend interactions prior to the experiment, that the observed values of this test statistic, which is kind of they use a complicated test statistic I won't get into, is outside of the 95% null interval under this permutation of treatment assignment. So that kind of follows this pattern before that we looked at, where we choose this test statistic that seems to measure interference or spillovers, but then we still go through this whole same procedure where we permute this treatment vector, and we compute the value of the test statistic under this permutation. But notice we're now computing the value of this test statistic under a permutation, but I have no rule by which I was actually allowed to substitute in y obs here into this test statistic, because I don't have a sharp null hypothesis. So I actually don't know what y for w star is. I only know what y for w is, and my null hypothesis of direct effects but no spillovers does not tell me, is not sharp, so it doesn't tell me what that is. So this doesn't work and can result in type 1 error rates that are much too large, even in things as simple as dyadic networks. It doesn't require super dense networks. So what went wrong in this recipe is basically that these second and third hypotheses are non-sharp. And so what we could do about that is try to basically make those hypotheses sharp in some way. So that, and again, what sharp means here is that we're going to be able to fill in the entire table of these potential outcomes. That is that given that we observe a unit under one global treatment vector, that we know what we would have observed for them under all possible global treatment vectors. Okay. So one way to do that is actually to posit a particular model of the direct effects. So we could say that the outcome for some individual is a function of their own treatment, and the full treatment vector is just their outcome under no one being treated plus the direct treatment effect. And so everybody has the same treatment effect for being themselves treated, which is tau. We're just going to posit some treatment effect tau that's constant across everyone. And then this would allow us to go ahead, and now we have a sharp null hypothesis. Now we could infer under this null hypothesis that there is this tau but not this spillover. So just under this model, this is now a sharp null hypothesis. The problem is, of course, that we've now assumed that there's constant treatment effects for everyone in the network. So we'd like to avoid doing that. But, I mean, how would this method work? Basically, here we do the same thing as before, except that now we do have a way of filling in this test statistic under W star, because we have some function that takes the y that we did observe, the w that we did observe, and the y star, and gives us the y under W star, the y that we would have observed under that global treatment vector. Okay, so this could allow you to do things like basically as a function of some direct effect and some spillover or indirect effect, yet another name for this, we can say, okay, here is the acceptance region for these two parameters. But here we're doing inference for the indirect effect that requires that we consider constant direct effects, right? So we've abandoned some of the just complete non-parametric distribution-free characteristics of what we were doing before. Okay, so what we're going to do instead is conditional randomization inference, where we sort of construct an artificial experiment that's somewhat different than the randomization that we did, but will allow us to do valid inference. So in particular, one analogy here is, say, in a basic independent experiment where you have Bernoulli random assignment. Everybody gets a coin flip, right? It's totally valid to condition on how many units ended up treated, N1, and then do a permutation test where you're permuting the treatment assignment vector, even though in your original randomization you actually, N1 was random, but now you can condition on N1 and draw new treatment vectors that hold N1 fixed, and the test will remain exact. So essentially we're going to do the same thing in that we're going to choose a set of focal units, and we're going to then have a test statistic that only considers the focal units' outcomes. So the focal units are going to be some subset of the vertices in our graph. And then when we draw the permuted treatment vector, we're going to draw that vector such that all the focal units have the exact same treatment that they did in our observed vector, right? So we're going to condition on some parts of the treatment assignment vector in creating this randomization distribution. And so we repeat the rest of this. Okay, so the idea, the general case here is that we condition on some units getting the same treatments as we observed, such that the null hypothesis becomes now sharp. Actually, a more general version of this is that depending on how we specified the level sets for these potential outcome functions, we just need it to be the case that we condition on the people being in the same level set that they were in the observed data. And then we draw from the randomization distribution. So we can use any test statistic we like for this purpose. I mean, one that has some particular appeal is basically a regression of the observed outcome on the unit's own treatment and also on the treatment of the neighbors, which actually is also justified by if you were to imagine a linear and means endogenous pure effects model could also generate that as the score. But we can use any test statistic that essentially is going to be something that we think is going to be sensitive to deviations from this null of no spillovers. So how do we select the focal units? Any choice of focal units is valid. If only some of the units have outcome data, we probably want to look at them. And so actually that's the case in these examples of these randomized experiments in Get Out the Vote on Facebook, is that we're not able to merge the data for all Facebook users in the US with voting data. And so we only have a subset of the users with outcome data. So it seems like a good idea to use them or some subset of them as focal units. In fact, since there's only about 10% of Facebook users who seem like they should be eligible to be voting are linked, then that's actually a good set to use as the focal unit. So for the 2012 presidential election, we did a very similar experiment to the one that was conducted in 2010 and was published in that Nature paper that I was criticizing. And so we did the same thing for the 2012 presidential election, but we did it correctly. And so now the thing is, actually in this case it turns out to not make a huge difference, in part because of this idea that only some of the vertices have outcome data. And so since in their analysis they were only able to look at the outcome data for this small set of vertices, it means that a lot of this dependence was reduced. If you just only are looking at outcomes for 10% of the units, a lot of them are not friends with each other, or at least the network is not nearly as dense as you might be worried about otherwise. So that helps a lot. But I think in general, this can be very important, as our simulations show. So we detected the main effects of that, but we're able to also reject the null hypothesis that your friends' treatments do not affect your voting. So we detect a significant effect of your friends being treated with this Get Out the Vote banner on you actually voting. So for every person who's directly induced to vote, basically, about 2 friends are induced to vote. So pretty large effects. I also have some software that implements this conditional randomization inference on my GitHub. One thing I wanted to finish by talking a little bit about, because I think some of this stuff might be interesting to this crowd in terms of the graph aspects of this all, is how do we pick the focal units in the case where there's not an obvious way of picking them because only some of them have data. So how do you decide whose outcomes to look at and thus whose treatments to hold fixed as you redraw this randomization from this randomization distribution? So one approach would be to find a maximal independent set or an epsilon net with epsilon 2 is equal to 2. And so then you would have a bunch of focal units that don't have peers in common. So that means that these focal units can have all of their peers' treatments are still varying under the randomization distribution. So that seems to give you more power. That might not select enough focal units, especially in a dense network, because very quickly you find the maximal independent set is like 8 people or something. So another approach would be to sort of keep going after you find the maximal independent set and select units who don't have a lot of edges to other focal units. So I think this is an interesting area to think about for folks who work on algorithms and graphs. So we did a bunch of simulations looking at just a particular ad health network with different test statistics, different direct effects and spillover effects, and these different ways of selecting the focal nodes. And so one thing that's good is that even when there's a direct effect, as long as the spillover effect is 0, that we have the correct type 1 error rates, right? So the size of the test is correct. These tests are exact. And then the power is really greatly affected by the choice of the focal nodes and the test statistics. So we recommend using something like the score test statistic that I showed earlier, and also that it can be helpful to select the focal nodes using something like this, finding this maximal independent set or something along those lines. So this whole setup, as I've discussed it so far, I focused on the case of just detecting any spillovers, where that is the null hypothesis that we're trying to test is that there might be direct effects of a vertice's own treatment, but there aren't other spillover effects. And then we focus on test statistics that look at those people's friends, because we expect those to be the strongest effects, right? But you could also be interested in testing higher order hypotheses, like, okay, yeah, maybe there's like spillovers from your friends, but there's not spillovers from friends of friends. Or I have two different networks, and I'm interested in whether one of them is sort of sufficient for capturing whether there are spillovers or not, et cetera. And so in that case, you need to condition on a little bit more in order to have the null hypothesis be sharp under this modified conditional randomization distribution. And so if we think about now we're testing for second order spillovers, and we have a focal unit A and a focal unit B, then we sort of end up with these units that are not that are sort of buffers. So they're not units that are having their treatment permuted anymore, but they need to have their treatment fixed in order for us to remain in the same level set for each of the focal units. And so you end up with these buffer units. One of the conclusions from this is if you're testing different hypotheses, you may want to select a very different set of focal units. Because if you're testing this higher order hypothesis, it might actually be good to have the focal units be clustered together, because then you won't be wasting so many vertices as these sort of buffer units that are neither providing power via the randomization, nor are they providing power via their outcomes. So but that's just sort of an intuition there. So overall, I mean, this works for many null hypotheses, so like no second order spillovers, et cetera. One of the challenges is as you get into these higher order hypotheses, you start doing a lot of conditioning. And so it can be the case that there's not much variation in your treatment vector that's left. And if there's not much of that left, that may really limit your power for some of these higher order hypotheses. But that kind of makes sense. So there's definitely some open directions here, including ways to better approximate some of the randomization that we have to do here, these sort of complex permutation tests, finding the optimal set of focal units. In a lot of cases, I mean, this has many advantages over asymptotic inference in that it's exact and distribution free, but it also, you pay a big cost in terms of power and other things here. So it'd be great to see further developments in asymptotic inference as well. So, so I think there are some interesting problems here, including alternate ways of selecting the focal units, simulating other kind of designs, and other ways of selecting these focal units. So anyway, that's it. Thanks. Yep.
Hi. So I'm not an expert in causal inference or randomization, so perhaps there's an easy answer to this. But I guess I would be worried that if you're choosing the focal units based upon the network, and because you might be looking for people who would fall into an independent set, that might bias things. You might find people who are less popular, and maybe these popular people are more likely to be persuaded or persuade, et cetera. Could you talk about that?
No, I think that's a good point, and maybe this will help clarify that. So because what we're doing is null hypothesis testing here, if we reject so the test will be valid, but they may only be sensitive to certain departures from the null. So if it happened that we pick the people who aren't susceptible to influence as the focal units, that would be an issue, because now we would have no power against the alternative. But we would still have the correct size for the test, the correct type 1 error rate. So the choice of the focal units could also be informed not just by sort of the structure of the graph, but perhaps a priori about your theory about who should be susceptible, because that could give you more power. But again, that highlights that, if you fail to reject the null hypothesis in a setup like this, where you don't have explicit guarantees for your power against certain alternatives, then there's not necessarily a ton that you can conclude from that. So I think the worry would more be that you incorrectly retain the null hypothesis, but in some ways that framework is not set up to handle that super well. But so any choice of focal units will be valid for testing the null hypothesis, and will give you valid, as in giving you the correct type 1 error rate, but it may be some choices of focal units, some choices of test statistics are not going to have power against perhaps the alternative hypothesis that's true in your data. So, yeah, Patrick.
Yeah, so my intuition is that with a Facebook scale network, you're basically always going to reject the null. Is that the case? I mean, you have a huge sample size. I would expect you would always get.
I mean, I would say, like, I mean, in this example I gave you, we sort of barely reject the null here. So, I mean, this is the, I think this is the 90 and 95 interval, something like that. So, I mean, yeah, we kind of reject the null, but it's like, that wasn't easy to reject the null there, right? And this is essentially with about 12 million observations or something like that, because it's only the people in the U.S. who are exposed to this treatment, but also, or exposed to the random assignment, but also we were able to link with their voting records. So,
I guess a related question is how easy is it to estimate the effect size and quantify the error in that estimate?
Right. Yeah, so this framework on its own does not allow for, say, estimating confidence intervals. You could consider ways of inverting these tests to produce confidence intervals, but then that would be inverting the test usually for a specific parametric model that makes provides a bunch of other sharp hypotheses, right? So if we posit that that the spillovers actually go according to some model like this, where it's basically the fraction of your friends is the normalized adjacency matrix that are treated that matters, then if you make those assumptions, then yeah, you could invert that test. But then you're back in this world of, yeah, I have a sharp null hypothesis, but now I need to assume constant effects everywhere. So that's still an open problem. But I would say it's not the case that necessarily, I mean, often with big data, we're interested in smaller effect sizes. I think one of the slogans we used to have on a coffee mug at Facebook was, with great power comes small effect size. So in part because you get interested in smaller effects, because, I mean, some of these interventions are very small, and the outcomes, like somebody actually going to vote, that's like a pretty big outcome to move for just showing them a little banner. So, yeah. Anyway, thanks a lot.